So now let's start with the dimensionless number. So as we have seen in the interface flux that for to account for experimental observation we have taken help of three equations. For momentum transfer we have taken help of Fanning equation. For mass transfer we have taken help of Slattery equation, and for heat transfer we have taken help of Newton's law of cooling. These are the three equations. The driving force in case of momentum transfer is the velocity difference. The driving force in case of heat transfer is the temperature difference, and the driving force in case of mass transfer is the concentration difference. The unit of the driving force is quantity per unit volume, as in case of mass transfer, which is kilomole per meter cube. The unit of driving force in heat transfer and momentum transfer is not consistent as per our assumption. So to account for this unit inconsistency, we make some necessary assumptions in Newton's law of cooling and Fanning equations. We multiply and divide Newton's law of cooling by rho Cp, and we multiply and divide Fanning equation by density. So as we have got the interface flux equation in this format, that is interface flux equals to transfer coefficient into difference in quantity per unit volume, we get transfer coefficient in mass transfer as Kc. In heat transfer we get transfer coefficient as H upon rho Cp, where Cp is the specific heat capacity, rho is density, and H is the heat transfer coefficient. In momentum transfer we get transfer coefficient equals to half FVCH, where F is the friction factor and VCH is the characteristic velocity. The unit of all these transfer coefficient are meter per second. So now let's see our first dimensionless number. The first dimensionless number that we will be dealing with is the Stanton number in heat transfer. So Stanton number in heat transfer is the generalized transfer coefficient in heat transfer upon generalized transfer coefficient in momentum transfer. The generalized transfer coefficient in heat transfer is H upon rho Cp, and in mass transfer and in momentum transfer it is VCH, because we consider here VCH because this 1 by 2 F is a constant, its value is constant, and it is also dimensionless. The VCH only has units, so we consider VCH. The physical interpretation of Stanton number in heat transfer upon interface flux in momentum transfer. The Stanton number, similar to this, the Stanton number is mass transfer is generalized transfer coefficient in mass transfer upon generalized transfer coefficient in momentum transfer. Stanton number in mass transfer is Kc by VCH. Physical interpretation of Stanton number in mass transfer upon interface momentum transfer. So now let us look at the relationship between interface flux and molecular flux and the dimensionless number emerging from their relations. So as we have defined in the previous slide, that interface flux equal to transfer coefficient into difference in quantity per unit volume, and as we know that molecular flux equal to diffusivity into gradient of quantity per unit volume. We know gradient of quantity per unit volume is the difference between quantity per unit volume upon its characteristic length. So by these three equations A, B, and C, we found out that interface flux upon molecular flux equals to transfer coefficient into characteristic length upon diffusivity. So now let us see this table. So in this table there are momentum flux, heat flux, and mass flux, and there are corresponding properties. So as we have seen in previous slide, transfer coefficient in momentum transfer is 1 by 2 FVCH, transfer coefficient in heat transfer is H by rho Cp, and in mass transfer it is Kc. Diffusivity in momentum transfer is mu by rho, or it is also called as kinematic viscosity. Diffusivity in heat transfer is K by rho Cp. It is called as thermal diffusivity, and diffusivity in mass transfer is DAB. Interface flux upon molecular flux equal to transfer coefficient into characteristic length upon diffusivity. For momentum transfer, we get this following equation, where 1 by 2 F rho VCH is its transfer coefficient, its diffusivity is mu by rho. By substituting appropriate values in this equation, we get this equation for momentum transfer. As we know that Reynolds number is rho VLCH upon nu, we substitute it in this equation. We get 1 by 2 FRE. In energy, in heat transfer, by substituting the appropriate values in this equation, we get HLCH upon K. So here this HLCH upon K is also called as Nusselt number. In mass transfer, by substituting the appropriate values of thermal coefficient and diffusivity in this equation, we get the dimensionless group to be Nusselt number in mass transfer, or it is also called as Sherwood number. So now let us see relationship between few more dimensionless number. So Prandtl number is momentum diffusivity mu upon thermal diffusivity. So we know that momentum diffusivity is viscosity upon density, and thermal diffusivity alpha equals to K upon rho Cp. So this comes out to be mu Cp by K. So this is the Prandtl number. Nusselt number, as we know, it is as derived from the previous slide, it is HLCH upon K. Schmidt number is the ratio of momentum diffusivity upon mass diffusivity. So this comes up to be mu upon rho DAB. Nusselt number in mass transfer, or Sherwood number, as seen from the previous slide, it is KCLCH upon DAB, where DAB is the diffusivity and LCH is the characteristic length. The Stanton number in heat transfer is related to Nusselt number, Reynolds number and Prandtl number by this relation. Stanton number in heat transfer equals to Nusselt number upon Reynolds number into Prandtl number. So by substituting appropriate dimensionless number, we get Stanton number as H upon rho Cp VCH. Stanton number in mass transfer is related as Sherwood number upon Reynolds number into Schmidt number. Stanton number in mass transfer comes out to be KCLCH upon DAB.